Now this video is just to add into the Poisson approximation for the binomial. So there's the avonford star, there's a nice little article. Pause the video to read it now because I'm just going to carry on regardless. So avonford star, and basically there's 60,000 people and there's been 5 cases of someone having got this disease. Now do bear in mind, if the disease is infectious, that effectively they won't be independent in real life. We're going to treat them as totally independent, but if it's infectious and you get it, then probably your family members get it, so on and so forth. So just be cautious of it because it might not necessarily work, but we're just doing an approximation at the moment. So we know that there's a 40,000 chance of actually getting the disease. So here what I can say is that X is binomially distributed with 60,000 people in the town and a chance of getting it being 1 in 40,000. And so what we're going to look at is not necessarily a chance of exactly 5 people getting it, but the chance of more than 5 people getting it, because that's the important bit, because they've said, oh look, lots of people have it. So not 5 exactly, but more than 5. And if you remember that the probability that X is bigger than or equal to 5 is going to be 1 minus the probability that X is less than or equal to 4. So in essence what we're going to look at is the probability that X is less than or equal to 4. Now this is a little bit of a side because actually the whole point of this is that I want to actually have a look and link it into the Poisson distribution. If we were to do the probability that X is less than or equal to 4, we'd find actually it's pretty tiny anyway. But we'll have a go because I want to set up the criteria. So my first option is it's going to be, I can't even think, not 30, 60,000 C0, and then the chance of 39,999 out of 40,000, and I'm just going to set this up with 1 over 40,000, that's 4,000, I want 40,000, and I'm just going to copy it before I put numbers in. So in our first example we're having 60C0, which means no one's got the disease, and so this will be to the 60,000, and this will be to the 0. So effectively I've got 39,999 over 40,000 to the power of 60,000. And so my next one, I'm going to have one person have the disease. And you can see why I wanted to copy it, it'll make it that much quicker. So this is 1, which means that 59,999 have the disease and haven't got the disease, and 1 does. And then if I do this again, we go down the route. This time I'm going to have the 2, and you can see the binomial structure that I'm using, so 5, 9, 9, 8, and a 2 there, and it'll just carry on. So 0, 1, 2, I'll fill in the... Now, using a calculator I can add all of these up, because this will be the probability of 0, 1, 2, 3, 4, and then if I do 1 minus that, I'll get my answer. So 1 minus everything in here gets me my answer. And the actual answer that it comes out to be is incredibly small. So that's going to be 1 minus, where was my solution? Here we go, 1 minus 0.981, which comes out to be, where am I? 0.019. So a very small chance of it happening, but it could happen. Now the whole point of doing this was not necessarily to answer this question, but to look at the actual structure. So you've got a context for the question, and I'm going to look at this structure, because we're going to approximate this with the binomial. So if I just erase this, and I'm going to go to a little bit of a side and ignore this previous bit, because actually what I want to look is the structure of this. So that's a binomial structure, and I'm going to convert it into a Poisson structure. Now to do that, what I'm first going to do is have a look at these values. So this to the 0, well that's just 1, so I'll get rid of it. And anything C0 is again just 1, so I'll get rid of that. So I'm left with this value here, which is a fixed value. So what I'm going to do is I'm going to call that a value of k. It's irrespective of what the number is, it's just a number that's fixed. So my next line, which is 60,000 C1, which again just comes out to be 60,000. So that is 60,000. And this bit is 1 over 40,000, which again, that's just 1 over 40,000. And so what I'm just going to do is take this and rearrange it. So that 1 over 40,000 I'm going to bring over to this side, because 60,000 times 1 over 40,000 is 60,000 over 40,000. And then again, I've got it times by this number. Now, this number isn't really much good to me because it's not my value of k. But if I say, well, hang on a moment, if I multiply this again, and let's say we multiply it by another one on top and another one on bottom, then I should get that number. However, I do need it to be like this, so what I'm going to do is say, well, hang on a moment, that value there, well, if I change this to make it 60,000, then to get from that number to 599, what I need to do is I need to divide by a 39,999 over, and times by rather, a 40,000. And so then I have this section here, and this section, if you remember, well, that is just my value of k. 40,000 over 39,000, well, that bit is approximately equal to 1. And so what I have now is I have 60,000 over 40,000, which is 1.5, times by k. So my first number was k. My second number is 1.5k. My third number, and here's where it comes on through again, so 60,000 C2, well, that is 60,000 multiplied by, so 60,000 multiplied by 59,999 over 2 times 1. This number here, 39,999 over 40,000, well, that number, again, I can actually link it into this original value of k. Because to get from here to this one, if I divide it by 39,999 squared, and then times it by 40,000 squared, then actually I'll drag it down a further 2. So, just as a little bit of a side, that is 60,000 over, times 59,999 over 2 times 1 multiplied by 39,999 over 40,000. Now remember, each of these are going to be to the 60,000s, which is why it's all in the brackets. So if I divide this side by 39,999 squared times this side by 40,000 squared, then actually that bit will cancel with those, and together I will get, all in all, my value here, which is 59,998. So let's just tidy this up a little bit, and let's get rid of the squareds there. So all of this now works out, and here again is my value of k, and what I end up with is approximately, and it's not exact, it is approximately, so 60,000 times about 60,000 over 2 times 1 multiplied by my value of k, which I've got there, and this bit and that bit, well, the top lines will cancel, so the 40,000 squared and the 40,000 squared cancels. So on the denominator, I'm going to have times by 39,000, oh, I've missed off a 9 there, 39,999 times by 39,999, and again, both of those are approximately 40,000. So divided by approximately 40,000 times 40,000. And 60,000 over 40,000, well, that is 1.5. So they'll cancel to be 1.5, which gives me 1.5 squared over 2 factorial times my value of k. Now, if I then carry this on for the next one, and I should be a little further along, so if I then carry it on for the 60,000 here, what I end up getting, if you follow through the same maths, is I'd get 1.5 cubed over 3 factorial times k. Now remember, as we were going through this, what we had was we had a binomial distribution, and the binomial distribution was given as that, where our expected value of x, and I'll start moving into green now, where e of x is np. So that's 60,000 times 1 over 40,000, which is approximately, well no, in fact in this case it's exactly 1.5. And if you remember back to earlier on in the Poisson distribution, when I was doing the videos for that, we linked it into our little sequence for e to the x. And so what I'm going to get here, because I've got the 1.5, is I'm going to have a starting value of k plus my 1.5k plus my 1.5 squared over 2 factorial k plus 1.5 cubed over 3 factorial k. And if you remember back to that, I then said, well, hang on a mo, we've got a value of lambda. So if I take my k out here, I get 1 plus 1.5 plus 1.5 squared over 2 factorial plus 1.5 cubed over 3 factorial. And the next one will be 1.5 to the 4 over 4 factorial, so on and so forth. And this part here actually linked into a value or a sequence which you didn't know until further maths, so your FP1, FP2, and that comes out to be e to the x, or in this case e to the 1.5. Now this value here of e to the 1.5, that was the basis for our Poisson distribution. And you should all know that if you add up all the probabilities of a Poisson distribution, they come out to be 1. At which point I can then link this in and say, well, hang on, the value of k in that case is going to be e to the minus 1.5, because it's 1 divided by e to the 1.5. And what I end up with is my nice Poisson distribution, where I have e, and I'll just go a little bit further up. So I have e to the minus 1.5, e to the minus lambda, plus lambda e to the minus lambda, plus lambda squared over 2 factorial e to the minus lambda, so on and so forth. And so this actually does link in to a binomial distribution. Now, obviously, our criteria. The video you watched was from examsolutions.net, and do bear in mind, it only works when n is large, p is small, and NP is not too large. And the criteria for not too large is basically less than or equal to 10 for the MEI. The exam solutions links into the Edexcel board, which is very similar, but there are slight nuances, differences and stuff like that. So in this case here, that's just a practical example of how to get from our Avonford star with 60,000, showing you effectively how you do the question, but then also linking in all of these values to how they'd set up to get an approximation for our Poisson distribution.